Okay, so in this video we're going to do MA 268 Algebra 3's Week 2, Question 1, which says that if P is a prime, so let P be a prime, and let G be a group of order P, show that G is cyclic, right? So we want to show that the order of G prime implies G cyclic. And maybe not so obviously, this is quite difficult, right? And I think the way to do this, as far as I can tell, is use Cauchy's theorem. So what does Cauchy's theorem says? Cauchy's theorem says if G is G finite, and a prime P divides the order of G. Yeah, I can see why they don't like this notation. They prefer to use the hashtag G, right? We'll use hashtag G as well. Okay. This means the same thing. It's just the order of G, and P divides the order of G. Then it says that there exists G in little g in G, such that the order of little g equals P. So if you have a finite group and then a prime number divides the order of the group, then there is an element G in G, little g in G, with order P, order that prime. Okay, well, this makes it straightforward because G has prime order. Let's say with prime P. Yeah, so this G, the order of G equals some prime P. Then we can just use this P, and then we know that there is some element in G with order P, right? And so let G element of G have order P. Well, if it says order P, the group generated by G also has order P. Okay, so but it's contained in G, right? So the group, but then it's contained in G. Contained in G. But because this is contained in G, they're both finite and they have the same number of elements. They must be equal, right? So that implies that G is the cyclic group generated by G. G is, and so and thus G is cyclic. So we're done. But kind of as like maybe an end thing, like I kind of feel like I've cheated here, because it says later on that, oh, for this exercise you may assume Cauchy's theorem. Does that mean for this exercise I have to do it some other way? So a little earlier I tried to do it myself and it failed, right? So I tried to do this. So I tried to use the contrapositive, and that G is acyclic implies G is composite. Think about, what do you call it? The order of G is composite, right? Which is the contrapositive. And then from here, because it's acyclic, if we have some element in it, right? And then suppose it generated G. We use this fact that we used here, right? That if it generates G, then it's equal to G, right? So the cyclic group generated by G, if it's contained in G and has the same order, then it is G. And obviously it's going to be contained in G because what do you call it? The group generated by an element in G is going to be contained in G by closure. But then that means that for any G, the group generated by G, the order of it can't be equal to G, right? Otherwise, G would be prime. Does that make sense? Wait, why? Acyclic plus composite. What was my argument again? Like, what was I doing? No, that would be prime. Sorry, what I was saying is, like, if it was equal, then it would. Sorry. Okay, so if we say there's some element in G, so the group generated by G has the same order as G. That means the order of G is the same as the order of G is the same as the order of the group. Then the group generated by G is equal to the group itself, and so the group is cyclic, contradicting acyclicness, right? And so the order of the group must be less than the order of G must be less than the order of the group, right? Which is what I wrote here. For every G, it has to be less. But also over here we can check that the trivial group is cyclic. And so we know that the order of G must be, because it's acyclic, it must be bigger than 1. And so since it's bigger than 1, we can pick a G with order bigger than 1, right, in G. Because it must be an identity element, and any other element must have order bigger than 1. So there is an element G, little g in the group, that has order bigger than 1, but less than the order of the group itself. And now by Lagrange's theorem, right, we have that the order of little g divides the order of the group. The order of this subgroup, right, divides the order of the group. And so we have G is composite by Lagrange's theorem. So this is Lagrange, which says that the order of this group generated by G, which is a subgroup of G, divides G, so it's composite, because bigger than 1, less than G. Also, Lagrange's theorem is way like super OP, and it's not proved using any of this. It's proved using cosets, so there's no cheating involved. So hope you enjoyed it. Thanks for watching.